Welcome to video 3 in chapter 6, where we will be discussing the mean and variance of discrete random variables. So we're going to look at a few examples. Now, what we've got here is a probability distribution table of our discrete random value x, for instance. So little x1, little x2, little x3, dot, 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 all the way up to little x sub n. These are all our individual values that we may have. And for each of those values, they have an associated probability. Now, the mean of x, of capital X, the actual discrete random variable, is nothing more than just multiplying each individual value with its probability, and multiplying those, and multiplying those, and multiplying those, and then adding together all of those individual all those individual results. Okay, so that's nothing more than the mean. And we'll talk about some shortcuts that we could use with the calculator to do all of this hard work for us. But that's the main idea behind the mean. So mu sub x, the mean of our discrete random variable x. Okay, again, it's nothing more than just multiplying each individual value with its probability and adding all those individual things together. So this is kind of the shortcut way that you could write all of that out, where our capital sigma here is our sum, x sub I represents the individual x's times the individual probabilities. The symbol for our variance is sigma squared, and we have sigma sub x because we're specifying of what we want to take the variance of. So sigma sub x squared. And so this is the formula, which we're not really going to have to use, but we will have to pretend like we're using it in the long run. So therefore, our standard deviation is just sigma sub x. And to calculate the standard deviation, we're just going to take the square root of our variance. Okay, if we take the square root of the variance, the square root and the square knock each other out, and there's our sigma sub x all over again. So let's do some examples so you can see how this is actually going to work out here. So it says calculate the mean and standard deviation for each of the following discrete random variables and identify them on the probability histogram. So the distribution of the count x of heads in 4 tosses of a balanced coin was found to be, so if we toss a coin 4 times, we could end up with no heads. We could get 1 head, 2, 3, or all 4 tosses could be heads. And here are the probabilities. These are the actual probabilities for that actually happening. Now I've already got the probability histogram over here, and you can see that our distribution is symmetric. We might also venture to call it approximately normal, which is fine. And so if we were to calculate the mean, here's again what we're going to have to do. We're going to have to multiply each individual value. So you can see right here, here's getting 0, and there's its probability. And so there's that part right there. And then if we add to it, getting 1 head with its probability 0.25, and if we add to that, 2 heads is 37.5%, so we multiply that, and so forth on down the line here, 3 and 25%, and last but not least, getting 4 heads, oh, different color, getting 4 heads is 6.25%. So if we multiply all those things out and add them all together, we should get a mean of, oh, wrong button. Wrong button. Come on, work with me here. Work with me here. There we go. We should get exactly 2. Okay, so where's 2 at on our probability histogram? Well, that's right in the middle. That's kind of what we would expect, right? If we have a symmetric distribution, the mean should be right in the middle, and the median should be right in the middle. So that kind of makes sense from what we've talked about previously. So now let's erase all this here. So now for the variance. Okay, here's the format it's going to look like. So we're taking each individual probability. So here's our 0. And from that, we're going to subtract the mean. Okay, so here's our individual x. Here we're going to subtract away the mean. So we have to get that mean from up here. There's that 2. And then we're going to square that quantity. And then we take that quantity and we multiply it by the probability for getting that specific value of 0. Okay, so there's kind of 3 parts to this, 3 numbers, but the one number, the 2, is going to repeat itself every time because it's always the mean. So then we look at the next part. We've got our next individual value was 1. There's the 1. We're going to subtract away the mean of 2 again, square that value, and now multiply it by its probability, which was the 0.25. And we keep on going down the line here until at the very end we get 1 exactly. Sweet. So the standard deviation would just be the square root of 1, which is 1. Done. Okay? So the amount that the number of heads deviate from the mean by of 2 is on average to be 1 head that we would deviate from on average. There's our standard deviation definition. So this is working it all out the long way. Okay, now I'm going to show you more the abbreviated version, what we can get by with. So Binford's law, the distribution of the first digits of numbers in legitimate records. Okay, so let's say you go to the doctor's office, your name probably has a specific account number tied to it. Okay, and the probability that your account number begins with a 1 is about 30%. And that your account number begins with a 2 is 17.6%, all the way down to if your account number begins with a 9, only happens about 4.6% of the time. So this is a legitimate thing. I'm not making up Binford's law, but this is a legitimate thing if you want to look it up to see what it's really about. So if we wanted to calculate the mean, here's what we can do where we're going to start using our calculator. Okay, so go ahead and list 1. Put in all the first digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9 in their own entries. And then in list 2, go ahead and put in the probabilities with, side by side in the same order that you put in 1 through 9. You need to put the 0.301 all the way down to the 0.046. Okay, so we're going to make it look like we did everything by hand, but we're really going to let the calculator do all the hard work for us. So the mean. Here's what we're going to do. We're going to do the very first part and the very last part. So I'm not really going to write out 1 times 0.301 plus 2 times 0.176 plus 3 times 0.125. Here's how we're going to make it look. We're going to do the very first part again. So here's the individual x times its probability, and then we're just going to skip everything in between. And we're going to do plus dot dot dot. And so here's dot, 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 dot. So we're skipping over all of this, okay? And then we're going to go to the last part. So the individual value was 9, and the probability was 0.046. This is what I would call the abbreviated work. And this is what you're going to have to do on, say, your homework, on the test, on the AP exam. This is fine because you're showing you understand what the mean really means, no pun intended, that it's the individual values times their probability and you add all of them together. So this is what I would consider your abbreviated work. Now we need to know what that equals, but we're gonna sit tight because I'm going to show you with the calculator how we're going to get the mean and the standard deviation all in one shot, and then we'll just come back and write the answer up here. All right, now your abbreviated work for the standard deviation. We're going to go ahead and start off with the square root. All right, now this looked kind of like what we did up here, but not exactly. So it worked by taking the individual value minus, we had to subtract the mean, but we don't know what the mean is quite yet. So we're going to come back later and fill this spot in here. So let's just do this. I'm going to highlight this green where the mean's going to go, because I need to go put that number in right there later. So I would take my individual value minus the mean, which we don't know what it is yet, but that's okay. We'll come back later and fill it in. And we're going to take that quantity and square it, and then multiply it by its probability, which was 0.301. Okay, so we're done with the first part. And to that, we're going to add dot, dot, dot. We're going to skip all of our stuff in between. You're showing you understand the basic format for how this works here. And then we're going to put in our last part down here. So we're going to repeat the same kind of format. So it was the individual value, which our last individual value is 9, minus, we need the mean again, so we're going to come back later and just fill it in right there. We square that difference there between our individual value and our mean, and we're going to multiply it by its probability, 0.046. So let's extend our standard deviation there, and we'll get that number here in a bit. So I'll just highlight this spot where we're going to put the standard deviation. So again, this is your abbreviated work for the mean up here. This is your abbreviated work for the standard deviation down here. Again, you only got to do the first part, the last part, and you can put plus dot 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 plus in between. All right, so now let's use our calculator. So in your calculator, you need to hit the Stat button, go over to Calc, and we're going to do number 1. We've done this before. We've used this command anyway. 1 variable stats. Now, here's where things are going to be a little different depending on what type of calculator you have. If your calculator just pops up and says 1 variable stats, and that's it, like there's no table, there's no kind of menu feature that's asking you to fill stuff in. If it just says 1 variable stats, then what you need to do is click second 1, so list 1 pops up, and then comma, second 2, the shortcut for list 2. So if this is the only thing that's on your calculator screen, you're good. And go ahead and press enter. Otherwise, this is what your calculator is going to look like when you hit stat calc and do 1 variable statistics. Up at the very top, it's going to say 1 variable statistics, and then it's sort of like a menu command here. It'll say list, and then it'll say frequently, or frequent, should be frequency list, and then calculate. Okay, so for list, you need to put in L1. For frequency list, you need to put in the probabilities. So probabilities always go in your frequency list. L1 are the actual values. And then go down and press calculate. Okay, so those are your 1 of 2 options that you will come across. Either it gives you the option of putting in the list in the frequency list, or it doesn't, and you're just going to put in L1, L2. So now you're going to get a screen, and there's 2 numbers that we need here, the mean and the standard deviation. The very first thing is X bar. That is our mean. So if I look at that, I see 3.441. There's my mean. Now I can go ahead and fill it in up here. There's my mean answer. And I can go fill it in my standard deviation now. So 3.441 there, 3.441 there. And so now it makes it look like I did all my work for my standard deviation. Now the standard deviation is the sigma sub x that you see further on down towards the bottom, and I see 2.462 if I were to do 4 significant digits. So sigma sub x, there's our standard deviation. So we can let the calculator do really all the dirty work for us. We're just going to pretend like we did all the dirty work. Okay, so that's what you guys can do from this point on in terms of quote unquote showing your work. And this is perfectly acceptable on the AP exam, and it will be perfectly acceptable when you guys take the test at the end of the chapter. All right, the last example we're going to look at. Here's a simple lottery wager, the tri-state pick-3 game that New Hampshire shares with Maine and Vermont. You choose a 3-digit number. The state chooses a 3-digit winning number at random and pays you $500 if your number is chosen. How many 3-digit numbers are there in the sample space? So how many different possible tickets could you buy potentially? Well, if you've got 3 numbers you need to pick, how many numbers could you pick for the first one? Well, 10, 0 through 9. How many could you pick for the second digit? Again, 10, because I'm assuming they didn't say that you couldn't have repeat numbers. And for the third digit, another 10. So 10 times 10 times 10 makes 1,000 different possibilities here. What is the probability that your ticket will be a winner? Well, there's only one correct number out of the 1,000, so 1 out of 1,000 is the probability that we're a winner. Let x equal the amount that you win. What are the possible values of x? Now, we're not taking into account how much it costs to play. We're just playing how much are you going to win? Well, you're either going to win nothing, more than likely, or you're going to win the $500. So 0 and 500. In the table below, construct a probability distribution of X, the amount that we can win. So our outcomes, 0 and 500. Probabilities, well, we had a 1 in 1,000 chance of actually winning the 500 bucks, which means we have a 999 out of 1,000 chance, or 0.999, of winning nothing. All right, so what is the ordinary average of the two possible outcomes? Does it make sense to consider that value as the average winnings? So normally if we had 0 and 500, well, the average of that is 250 bucks. Does that mean on average we're going to win 250 bucks when we play the lottery? No, that doesn't make any sense at all. We don't have a 50-50 chance of winning $0 and $500. That's why we have these weighted means here. Okay? So it gives the two outcomes equal weight rather than accounting for the fact that 0 occurs almost always and 500 rarely occurs. So 250 would be the answer if this was 50% and 50%, but not quite so much because these probabilities are very unequal. So the mean and the standard deviation. Again, you could do this, with your calculator. You could call this your new list 1. You could call this your new list 2. Or really, we could almost just kind of punch this into our calculator since there's only two possibilities here. So for the mean, we're taking our individual 0 times the probability, which, that's end up going to be nothing, right? Because that's 0. And then add to that the 500 times the 1 out of 1,000, and we get 50 cents. Okay, you should get 0.5 in your calculator. The standard deviation, again, we take the individual value and we subtract away the mean, which is 0.5 or 50 cents, square it, multiply it by its probability, plus the same thing, the other individual value minus its mean squared, times its probability, and that should give us $15.80. Okay, and you might think that's a really large standard deviation. Could that happen that the standard deviation is larger than the mean? And yeah, if we're talking about between $0 and $500 and the mean's 50 cents, there is a huge deviation between the mean and $500. That's where a lot of this $15.80 is coming from, is because of that large deviation between there. Okay? Oh. All right, so is this lottery fair? Well, if in the long run you expect to only win 50 cents, and let's say this costs you $1 to play, in the long run you're only going to be winning 50 cents for every dollar you give to the lottery people. So it's absolutely not very fair. So the expected winnings does not equal the cost to play. In the long run, they keep 50 cents per ticket purchased on average. Okay. Now, if you bought just one ticket, you're either going to win nothing or you're going to win 500 bucks. But in the long run, if you were to play this like some people I know, some older people like grandma and grandpas, they like to play the lottery like every day, every week, because someone's got to win. So in the long run, they're going to be losing money. So some observations here. If you play the Tri-State Pick 3 several times, we would call the mean of the actual amounts you win X bar. The mean mu sub X is a different quantity. Okay? So it is the long run average winnings if you expect to play a very large number of times. So mu was more of our population value. So that makes sense that if we play a very large number of times, that kind of represents the population. So that would be that amount. But if you were just to play, maybe 10 times, that's not a very large number. So the actual mean that you would win off your 10 times, we would refer to more to that as just X bar. That would be like a sample of the population. Now, another thing to notice is you may have seen that our mean value of 50 cents, that's not actually a value that's in our probability distribution table, which is fine. Okay? Very rarely will it happen to be that the mean is one of these two values, or one of many possible values that you could have in your table. And you will often find that the mean of a random variable x, mu sub x, is also referred to as the expected value. Okay? Because another way we could say this 50 cents is we expect to win 50 cents per ticket played in the long run. So sometimes you might see it referred to as the mean. Sometimes, probably more times than not, you'll see it referred to as the expected value. And that is all for video 3. We'll see you for video 4.